Good afternoon, students.
Good afternoon, sir.
Good afternoon, sir.
So I hope you have been communicated by your CR that coming Wednesday I shall be taking the practical class for inorganic chemistry, and on that day I shall also give you a home assignment for inorganic chemistry. Okay, and I shall actually form a Google Classroom where you will submit your practical assignment as well as the home assignment for the theory class. So, in our previous class, we have discussed what is octahedral site preference energy, octahedral site stabilization energy, and it is mainly the energy difference between the octahedral octahedral metal ion, right, or in a given ligand environment, and in the same using the same ligand, if the same metal ion was in the tetrahedral environment, then what is the CABC, and difference in CABC between octahedral and tetrahedral metal ion system is known as octahedral stabilization energy. Invariably, octahedral stabilization energy is positive because always octahedral complexes are more stable thermodynamically than tetrahedral complexes, but the degree of stability varies from D1 to D9, right? And we have seen what are the metal ions that where this difference is quite small, so that change of certain other parameters such as the temperature, solvent, etc., reaction condition may lead to isolation of the tetrahedral complexes. And we have seen that D0, D5, D10, where we have no difference in the stabilization between octahedral and tetrahedral because crystal field stabilization energy is 0 for them. And then we have seen that D1, D6, D7, and D2, these are the metal ions for which there is the OS AC is relatively small, and as a result of that, we may be able to isolate the tetrahedral complexes much more easily for this metal ions. But remember, this table is only for the aqueous ligand. So for each of the different ligand, we may form a different table, and there may be slight change from ligand to ligand. This table is valid for the water as a ligand, right? And in this diagram also we have shown that for D1 we have a very small difference. D2 we have more different. The OSC is larger. The difference in OSC and OST, tetrahedral stabilization energy is relatively larger, but still it is manageable. In case of D6, again it is quite small, and in case of D7, again it is somewhat larger, but for D3 or say for D8, the stabilization of the octahedral complex is so huge that tetrahedral complex is not very easily formed. So certain metal ions can easily form tetrahedral complexes where this gap is small. Certain metal ions are reluctant to form tetrahedral complexes where this gap between octahedral site and tetrahedral site is quite large. And next, we shall take one example of spinels or spinels, where we use this octahedral site stabilization energy to predict the structure of the spinels. Now, what are spinels? Spinels are generally mixed metal oxide, like say magnesium Al2O4. Now, you note that in the spinel, so we have 4 oxygen atoms, so altogether 8 negative charge, and to balance it, we will have 1 divalent metal ion and 2 trivalent metal ions. So spinels are oxides of binary metal ions. One of the metal ion is bivalent and other metal ion is trivalent, and the ratio of bivalent to trivalent metal ion is 1:2. Now, spinels, in the spinels, these oxygen atoms are arranged in such a way that they form certain pockets or certain holes are octahedral and certain holes are tetrahedral, and in these holes the metal ions which are relatively smaller in size, they reside in these holes or pockets or voids. Now, obviously, in terms of electrostatic interaction, if a trivalent metal ion occupies the octahedral pocket, then it actually interacts with 6 negatively charged ligands. And on the other hand, if the bivalent metal ions occupies the octahedral pocket, it will interact with 4 ligands only. So from electrostatic point of view, the most stable structure will be, and the observed structure will be, where the divalent metal ions sit in the tetrahedral pocket and the trivalent metal ions sit in the octahedral pocket, because in that way trivalent metal ion interacts with more number of ligands and so achieves more electrostatic stability. So for normal spinels, we expect the divalent metal ion, which is sometimes called A, because spinels are sometimes given this type of structure, A B2O4. So this is the divalent metal ion is A, trivalent metal ion is B. So A B2O4. So the divalent metal ion A occupies the tetrahedral site and trivalent metal ion occupies the octahedral site. And so for spinels, we may say we have this kind of structure: divalent metal ion occupying the tetrahedral and 2 trivalent metal ions occupying the octahedral holes, and there are the oxide ions. Now, under certain conditions, so this is the normal spinel where the trivalent metal ions, the 2 trivalent metal ions will occupy the octahedral hole. But there may be certain arrangements which arises mainly because of the crystal field stabilization energy, certain arrangements where the reverse thing is happening. That means these divalent metal ions moves from the tetrahedral pocket to the octahedral pocket, and instead one of the 2 trivalent metal ions leaves the octahedral pocket and comes to the tetrahedral pocket, so that you have a structure like BABO4, where B is the trivalent metal ion, A is the divalent, B is the trivalent. That means we have the trivalent metal ion occupying the tetrahedral pocket, one of the trivalent metal ion occupying the tetrahedral pocket, and another trivalent metal ion along with the divalent metal ion occupying the octahedral pocket. So this kind of spinels where one of the trivalent metal ion and the bivalent metal ion, they have exchanged their position, and the trivalent metal ion is now in the tetrahedral pocket and the divalent metal ion is in the octahedral pocket. That kind of spinel is called invert spinel. So spinels may have 2 kind of structure: the normal spinels where divalent occupies the tetrahedral and both the trivalent occupies the octahedral site, or invert spinel where one of the trivalent metal ion occupies the tetrahedral site and the other trivalent metal ion along with the bivalent metal ion occupy the octahedral site. So now question is, which type of oxides will have which type of structure. So let us take some examples. So FeCr2O4. Now in FeCr2O4, you see we have, so since we have oxide as the ligand in spinels, so all the metal ions except cobalt 3 can be considered to be in the high spin state. Now if I have a ferrous FeCr2O4, so that means we have a ferrous ion, we have chromium 3 ion, we have oxide. So for FeCr2O4, for the high spin ferrous, if you compare the CFAC of the high spin ferrous and if you compare the CFAC of the high spin, rather CFAC of the chromium 3 ion, you will find that we have this data already, that ferrous means D6, right? So for D6 you see, for the high spin, for D6 the CFAC is 4 DQ. negative of this, so it is minus 4 dq. CFSE is minus of minus 4 dq. CFSE is 4 dq. But for D3, it is 12 dq, right? So CFSE for the chromium is more than the CFSE of ferrous. And in terms of electrostatic interaction, chromium having 3 plus charge and iron having 2 plus charge, obviously chromium will prefer the octahedral site. So FeCr2O4 will have normal spinel structure because chromium 3, a D3 system, has got more CFSE value than the high spin ferrous ion, a D6 ferrous ion. Similarly, zinc aluminate. Neither zinc nor aluminium has got any CFSE, so it will be normal spinel. CO3O4, where we have a cobalt ion to cobalt 3 ion. Now all cobalt 3 ions are low spin and thereby has got a very high CFSE value, right? Low spin cobalt, you know, it has got minus 24 dq as the CFSE. So low spin cobalt has got huge CFSE, so compared to cobalt 2, the D7, and as a result of this, again, in case of CO3O4, which is actually 1 cobaltous ion and 2 cobaltic ion, so cobalt 3, because of its very high CFSE compared to cobalt 2 ion, it will remain in the octahedral hole, so it has got normal spinel structure. Again, if I take Mn3O4, we have manganese 2 ion and manganese 3 ion. Now manganese 2 ion high spin is D5, so it has got no CFSE. But manganese 3 ion has got D4, so it has got high CFSE, right? So again, if you compare the previous data, so as you can see, for high spin D5 we have 0 CFSE, but for high spin D7 you have CFSE equal to 8 dq. So sorry, high spin D4, we have to go to D4. So for high spin D4 we have plus 6 dq. So manganese 2 is high spin D5, manganese 3 is high spin D4. So for manganese 2 there is no CFSE. For manganese 3 it has got plus 6 dq as the CFSE. So since manganese 3 has got higher charge as well as higher CFSE, so we expect Mn3O4 to also have the normal spinel structure. Now if I go to Fe3O4, Fe3O4 means so we have the Fe3O4 structure. Fe3O4 means 1 ferrous ion, 2 ferric ion. Now ferrous ion high spin D5. So high spin D5 has got no CFSE. But high spin ferrous ion, it has got the energy equal to minus 0.4 dq. That means CFSE equal to plus 0.4 dq. So ferrous ion has got higher CFSE than ferric. So as a result of the crystal field stabilization energy, higher CFSE of ferrous compared to ferric, what will happen? That 1 ferric ion will move away from the octahedral site. It will go to the tetrahedral site, and the ferrous ion, in view of its higher CFSE, it will move to the octahedral site. So Fe3O4 is expected to have invert spinel structure, because in that way the ferrous ion having CFSE, higher CFSE, will occupy an octahedral site, and ferric ion having 0 CFSE will move to the tetrahedral site. So Fe3O4 will have invert spinel structure. Similarly, if I take say NiFe2O4, nickel 2, ferric 3,2O4. Again, ferric, as we have seen, it is high spin D5, 0 CFSE. Nickel 2, it has got T2G6 Eg2 configuration, so energy of the system is minus 1.2 delta O, CFSE is 1.2 delta O. So nickel has got quite high CFSE, but ferric has got 0 CFSE. So again, because of the stabilization of crystal field effect, one of the ferric ion will move away from the octahedral site to the tetrahedral site, and the nickel 2 ion will move from the tetrahedral site to the octahedral site. So we expect that NiFe2O4 like Fe3O4 will have inverse Spinel structure. So in general it is found that if the crystal field of the crystal field of the trivalent metal ion is lower than that of the divalent metal ion, we will have inverse Spinel structure, and this is nicely illustrated by your Fe3O4 or NiFe2O4 structure, which because of the higher stabilization of the crystal field stabilization energy of the bivalent metal ion like nickel 2 or ferrous, they move away from the tetrahedral site to the octahedral site. By that way, it generates more CFAC, and one of the tetrahedral metal ion, here the ferric metal ion, moves away from the octahedral site to the tetrahedral site. Right. Now, if I go to CO3O4, for instance, we have cobalt 2 high spin and cobalt 3 low spin. In this case, both cobalt 2 and cobalt 3 has got CFAC. But as I have told you, D6 low spin, all cobalt 3 except on the complex with fluoride are high spin, are low spin. So cobalt 3 being a low spin, its CFAC is hugely higher than that of the cobalt 2, the high spin D7. So as a result of this complex will have again the normal spinel structure, because cobalt 3 has got higher crystal field stabilization energy than cobalt 2. So it is quite easy to answer the questions which comes in the exam, that I will give you some complexes and or some compounds, some mixed oxides, and I will ask you to find out whether it will have normal spinel structure or inverse spinel structure. So you have to find out the CFAC of the divalent metal ion, you have to find out CFAC of the trivalent metal ion and compare them. And if we find that the trivalent metal ion has got the higher CFAC, then we will have a normal structure. If I find divalent metal ion has got the higher CFAC, then it will have a inverse spinel structure. And if there is no CFAC at all for both the metal ion, then again it will have a normal spinel structure. So if M3 ion has a higher CFAC in an octahedral crystal field compared to M2 ion, it will have a normal spinel structure. On the other hand, if the M2 plus ion, bivalent metal ion, has got higher CFAC in an octahedral crystal field compared to an M3 ion, inverse spinel structure of this kind will be obtained. So it is quite easy. Simply you have to find out the CFAC of the bivalent metal ion and CFAC of the trivalent metal ion, find out which one is higher, and then you have to say whether the structure will be normal spinel or inverse spinel. Next, we go to another application of crystal field theory, and that is explaining, say, heat of hydration of different bivalent or trivalent metal ion. Here we have taken bivalent metal ion. Now, what is heat of hydration? Heat of hydration, we may say, we may write it in this way. So, if we have a, say, metal ion, Mn plus in the gaseous state, 1 mole of metal ion in the gaseous state, and then if you dissolve it in water, right, say in XH2O, right, dissolve, and then the metal ion gets solvated, right, then the enthalpy change in this reaction is called heat of hydration, right? This is called heat of hydration. That means the energy change when 1 mole of isolated gaseous metal ion is allowed to be dissolved or allowed to be solvated in aqueous solution, then the change of enthalpy is called heat of hydration. And heat of hydration is invariably negative because on hydration, because of the electrostatic interaction between the dipole of water and the metal ion, electrostatic interaction, energy is released. So heat of hydration is invariably negative. Now in this plot, we have plotted minus in order to keep things positive. So minus, we have taken negative of the heat of hydration in kilojoule per mole, and we have plotted calcium. That means calcium is D0, right? And then we have scandium, titanium, vanadium, etc., divalent metal ion. So we have D1, D2, D3, D4, etc., D5, and this is D10. Now, thing is that we know that across, normally we should expect that across a period, as we go from calcium to zinc, we find that because of the fact that the nuclear charge is increased one by one, but electrons are being added to the d orbitals which are poorly shielding. So effective nuclear charge increases on going from calcium to zinc, and as a result of this, the radius decreases, and because of the decrease of radius and increase of the effective nuclear charge, the hydration energy increases. The enthalpy of hydration increases. That means more energy is released. And if there were no crystal field effect, we should expect a straight line between, say, D1, sorry, we should expect a straight line between this D0, D5 and D10. So if you join these three spots, D0, D5 and D10, we should get a straight line. So, like this. You should get a straight line. But in reality, what we get? A double hump curve like this. So you get this kind of, this is a hump and this is another hump. Why? Because from D0, then D1, D2, D3, the crystal field increases, crystal field stabilization increases. So for D3, you have initially the highest crystal field. Then for D4, high spin D4, crystal field stabilization decreases. D5, it is lowest. Again, if I go to D6, crystal field stabilization increases. D7, it increases. D8, it goes to the highest point. Then D9, D10. So because of the crystal field stabilization, what happens that we get a double hump curve, and these yellow lines correspond to the fact that what happens if I, from these points which are inclusive of the crystal field stabilization, if I deduct the crystal field stabilization. So after deduction of the crystal field stabilization energy, we get these yellow points. And you see, when we take away the advantage due to crystal field stabilization energy, then we find that the dots are more or less on the expected line, almost on the expected straight line. But if you include the crystal field stabilization, which is the real thing, we find that instead of a smooth straight line, we get this kind of double hump curve, and this double hump curve is arising because of the CFSE of this D3, D4, D5. You are not seeing D1 and D2 because for scandium 2+ and titanium 2+, these ions were then not, when this data was accumulated, when this drop was accumulated, this data was not available. So for scandium 2+, that is D1 and D2, data is not available. That's why points are missing. So you are getting D3, D4, D5, D6, D7, then D8, D9, D10, and you find from here that there is a double hump plot. And this double hump plot arises because of the effect of crystal field stabilization energy. If I deduct the crystal field stabilization energy from the hydration energy, then we find these adjusted hydration energies where the crystal field has been taken away, they fall in the expected straight line. But due to the effect of the crystal field stabilization energy, the plot is non-linear in nature and it is double humped. Similarly, if I compare the lattice energies of calcium oxide, titanium oxide, vanadium oxide, and manganese oxide, right? So calcium oxide is D0. This titanium oxide is actually D2, right? Vanadium oxide is D3, right? And this is D5. Now, normally from calcium to titanium to vanadium to manganese, the size of the metal ion decreases. And as a result of this, if there was no crystal field effect, we expect that as we go from left to right in this series, we expect crystal field stabilization energy to increase, right? There should be a smooth increase from calcium oxide to titanium oxide to vanadium oxide to manganese oxide. But in reality, the values are 3460. It increases hugely. It increases from D0 to D2, D2 to D3. It increases slightly, and for D3 to D4, you find for D3 to D5, you see the hydration, the lattice energy falls, and in fact, for manganese oxide, as you can see, that in spite of it having much lower size than titanium, manganese oxide, the lattice energy is actually almost comparable to that of the D2 ion, right? Titanium. Again, the reason is that calcium D0, there is no CFSE. Here there is CFSE. Here there is the CFSE is maximum D3. So you have the highest lattice energy here, right? And when you go to manganese D5, since the crystal field stabilization energy falls because it is D5, it has got zero CFSE. So you find that manganese oxide has got much lower lattice energy than vanadium oxide, and it has got lattice energy which is very much comparable to that of the titanium oxide. So this kind of data, lattice energy data, or crystal or the hydration energy data, can be easily explained in terms of the crystal field stabilization. If you take into account how the crystal field stabilization energy varies, then you can explain the nature of the non-smooth variation of the hydration energy or lattice energy across the period. Now, this is another application. Here we have plotted ionic radii. Now, the left-hand side plot is for the bivalent metal ion, and right-hand side plot is for the trivalent metal ion. And again, as I've told you, expectedly, what happens that if I leave aside the crystal field effect, so this is the D0 system, right? So this is the D5 system, and this is the D10 system. So if there were no crystal field effect, there should be a smooth straight line between. So actually, this should be D5, D10, right? This one. But what do you find? That in effect we have either this plot is for the high spin, this plot is for the low spin. So for high spin complex, we have variation like this. For low spin complex, you have a double straight line, right? Two straight lines meeting at this day 6 point. And for the trivalent metal ion, we have also very similar variation. And again, you can explain the things on the basis of crystal field stabilization energy. So as you can see here, for titanium 2, again, we don't have any data. So this is the D3. It has got the smallest size. Then when you go to D4, the CFSE decreases, and as a result of this, metal ligand bond distance increases. D5, there is no CFSE, so metal ligand bond distance is highest. Then again, when you go to D6, metal ligand bond distance decreases because the CFSE increases. D6, D7, D8, right, where you have the highest CFSE. And then if you go to D9, D10, CFSE decreases, and as a result of this, the radius, metal ligand bond distance increases and the radius increases. So these kind of changes, again, you can explain using CFSE. So here we have the highest CFSE for the high spin system, or the here. So you have the lowest metal ligand distance. So and then for D4, D5, D6, the CFSE decreases. So it goes on decreasing, right? It goes on increasing first of all, then it again decreases, because D5 to D6 there is CFS increases, D6 to D7 their CFS increases. So as a result of this, you have the lower metal ligand distance. D8 again CFS increases, so metal ligand bond distance increases, and from D8 to D9 CFS decreases, so metal ligand bond distance increases, so radius increases, and here also metal ligand bond distance largest. So both the curves can be explained using the CFSE model, where and if I go to low spin, then from low spin system, then from D3 to D4 you have CFSE decreases, D4 to D5 CFSE decreases, D5 to D6 CFSE decreases. So there is continuous increase of the CFSE, and as a result of this, the correspondingly the radius decreases. So D3 to D4 higher CFSE, lower radius, higher CFSE, lower radius. D6 you have the highest CFSE, so the lowest radius, okay, lowest radius. And then D6, so for the low spin system, D6 has got the highest CFSE, so the lowest radius is observed at the ferrous ion D6. And then D7, D8, D9 you have the crystal field stabilization energy decreases, and as a result of this you have the radius increases. So in this way, both high spin and low spin system, here also the very similar thing. You can easily go through, you can easily explain the ionic radii of divalent and trivalent metal ion, its variation, again nonlinear variation of the radius of the divalent and trivalent metal ion can be easily explained when we include the CFSE in our calculation. Okay. So this completes our discussion on the ligand field theory. Next we come to the molecular orbital theory. Now, before going to the molecular orbital theory proper, I first of all like to introduce. I know you have some introduction to the molecular orbital theory in your 12th class, 11, 12. Now, all of you are I think, are very much familiar with, where is that? This term. Do you know what is LCO?
Sir, linear combination of atomic orbitals.
Right. So you have learned the molecular orbital theory in your school days, and you have learned that LCO is linear combination of atomic orbitals. That means when two atoms A and B, they each of them suppose contains one electron each, and suppose the electron of A is occupying an orbital which is described by the wave function psi A. Electron of B is occupying an orbital which is described by the wave function psi B. Then in the molecule, when they combine, we'll have a molecular orbital which may be described as C1 psi A plus C2 psi B, which is called linear combination of atomic orbital. We are taking linear combination of the two atomic orbitals, and we are forming a new orbital which we may call a molecular orbital. And you can easily find out from simple mathematical calculation what is C1 and C2. That can be found out, right? So here again, and you also know from your knowledge of mathematics that I think by this time you are familiar with the Schrodinger wave equations, isn't it? In the physics class, you have been taught about the wave theory and all these things, isn't it? Hello?
Sir, we don't have physics in first semester.
But anyway, even the 12th class books, they have got this wave picture of the atom and the Schrodinger wave equation, Heisenberg uncertainty principle. Since you are good students, JEE pass student, obviously you know all these things, I suppose, isn't it?
Yes, sir.
You have some.
Yes, sir.
Some bit was on class
Okay.
11th too.
Okay, so you know that there is an equation called Schrodinger wave equation, and if you can solve the Schrodinger wave equation for a given system, you can get the corresponding energy values of the system and the corresponding wave functions of the system, and that describes the properties of the system. Now, from your knowledge of mathematics, you know that if for a differential equation, suppose we have three solutions, say, or say two solutions, second order, psi 1 and psi 2, phi 1 and phi 2. Now, if phi 1 and phi 2 is a solution of a differential equation, then you know that any linear combination of phi 1 and phi 2 will also be a solution of that equation, right? And as a result of this, you can take phi 1 and phi 2 as a solution, or you may take, say, C1 phi 1 plus C2 phi 2, and another, say, C3 phi 1 and C4 phi 2. These two solutions may also be taken as the two solutions of the differential equation. That you already are aware of the fact that linear combinations of the solutions are also solutions of the equation. So, in order to apply the molecular orbital theory for the complex, and you also know, in order to get good molecular orbital, there are certain conditions. What are the conditions? First of all, the atomic orbitals which are being mixed must be of proper energy, right? They must have comparable energy. Say you cannot get overlap of, say, a 2p orbital with a, say, 6d orbital or 5d orbital, right? It is very difficult. So the orbitals which are being mixed, which are being combined, they must have, first of all, comparable energy. Then only if the two orbitals which are being mixed are of same energy, then interaction is maximum. If the energy difference increases, then the interaction decreases, and if the energy difference become very large, then interaction also decreases, right? Almost like the human being. Then we also know that in order to have combination of atomic orbitals which are acceptable solutions, we must have the orbitals matching in symmetry. That means two orbitals which are being combined must have proper symmetry. Meaning, suppose we are having two atoms A and B coming together. You have to combine pz orbital with the pz orbital of A and B. You have to combine px orbital with the px orbital of A and B, and so on. But you cannot mix, say, pz orbital of A with say, px orbital of B or py orbital of B, because Z, X and Y, they are in other directions. Their symmetry is defined. As a result of this, a pz orbital of A cannot be mixed with the py or px orbital of B. So the second condition is that the orbitals which are being combined must be of proper symmetry. So they must have comparable energy, they must be of proper symmetry. And third thing, you know that the atomic orbitals being mixed, number of atomic orbitals being mixed must be equal to number of molecular orbitals produced. That means there is conservation of orbitals. If you mix two atomic orbitals, you must get back two molecular orbitals. If you mix 6 atomic orbitals, we must get back 6 molecular orbitals. That thing, again, probably these three things you are already familiar. First of all, the conservation of the number of orbitals, number of atomic orbitals mixed must be equal to number of molecular orbitals produced. Then the atomic orbitals which are being mixed must be of comparable energy. If they have very defined energy, then their interaction will be very low because they will not overlap with each other because of the difference of the radial distributions. And third thing is that they must have also proper symmetry, right? So you cannot expect to have overlap of a pz orbital with a px and py orbital, or you cannot have overlap of a dx minus y square orbital with the dz square orbital of another atom. So you must have orbitals which have matching symmetry. So with these three things keeping in mind, we propose, or we go to the molecular orbital theory of the metal complexes. Now, in the first step of the molecular orbital theory, what you have 6 donor orbitals of 6 ligands, right? They are actually sigma donor orbitals. So this is one, plus z direction, minus z direction, plus x direction, minus x direction, plus y direction, minus y direction. So we have 6 ligand orbitals, and using these 6 ligand orbitals to get proper symmetry match with the metal orbitals, we produce 6 ligand group orbitals. So they are ligand group orbitals, means these orbitals will not be confined to any particular ligand, but rather they will be ligand groups. That means at least 2 ligands will be involved. So just as I have told you, if I start with 4 orbitals, if I take linear combination, we must get back 4 orbitals. Similarly, since we have started with 6 ligand donor orbitals, because in octahedral symmetry we have 6 ligand orbitals, sigma type ligand orbitals, that are located in the plus x minus x, plus y minus y, and plus z minus z direction. So those 6 individual ligand orbitals have been combined in a mathematical way, and from those 6 individual ligand orbitals, we have constructed certain ligand group orbitals, right? These ligand group orbitals have been formed by, there may be 2 ways of forming these ligand group orbitals which are beyond our purview. One is using simple group theoretical argument. So there is a mathematical branch which is called group theory, and using group theory we can form these ligand group orbitals, or you can do simple quantum mechanical calculation to do this. And probably the easiest thing is to mix group theory with quantum mechanics and to approach to form these complexes, to form these group orbitals. We are not concerned with how they are formed. We are trying to see what are the 6 ligand group orbitals. So we have mixed 6 ligand orbitals, and the 6 ligand group orbitals are shown here. So you see in the first ligand group orbitals, how it is combined. We have got equal proportion of sigma x plus sigma minus x, means the ligand orbital which is located in the minus x point, right? Plus y minus y plus z minus z. So we have equal proportion of 6 ligand orbitals in 1:1:1:1:1:1 proportion, and we have taken contribution from all the 6 ligands, right? And this is the 1/√6 is what is called normalization constant, because you know that wave functions must be normalized, so you can forget about that. These are normalization constant, so that the wave function is normalized. So first ligand group orbital is this, where all the 6 ligands contribute equally, and you have a plus 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 sign. That means all with plus sign. So you see here you have a ligand group orbital where all the ligands has got contribution, and they have got plus 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 signs, right? That means uniform sign of the wave function. Now, before going to anywhere else, can you tell me, any one of you, this ligand group orbital is likely to overlap with which particular metal orbital? My question is, if I consider only this ligand orbital, ligand group orbital, the first ligand group orbital, which particular metal orbital is suitable for overlapping with it? Anyone? Any answer? No answer.
Sir, not sure, sir.
Huh? Not sure. Actually, it is written here. Because if I take an s orbital,
Sir, S orbital.
yes, obviously, because s, if I take a metal s orbital, it is spherical, and this is also spherically symmetrical, and s orbital has got everywhere plus sign. So you see everywhere it is plus sign, and here also these orbitals are actually surrounding it in from all direction with same sign. So this orbital, this ligand group orbital is suitable for overlapping with the s orbital. That's why I have written here the matching orbitals are written here. So with this ligand group orbital, the s orbital is the matching orbital. Next ligand group orbital. Yes. Any question?
Sir, this is lithium.
I don't get your point. What do you say?
Sir, those metal is lithium.
Lithium. Where from lithium is coming?
Sir, lithium has s orbital.
All atoms has got s orbital,
Oh yes,
Yes.
yes.
isn't it? Any metal atom, any atom has got s orbital. Starting from hydrogen atom to say element number 160, etc., etc., all of them has got s orbital, isn't it? Right. So you see next combination here we have Z and minus Z ligand orbitals. They are having positive contribution plus and plus with proportion of 2, and all other metal orbitals x minus x, y minus y, they have got half of the contribution of the Z direction, and they have got opposite sign. So Z and minus Z has got positive contribution, x minus x, y minus y, all of them has got negative contribution. So here you see Z and minus Z, they have got the positive contribution, that's why sign is positive, and x minus x, y minus y, they have got negative contribution, and this lobe size is ideally it is half of this here. So you can easily see here this combination, this ligand group orbital is very similar to dz square orbital, because for dz square orbital this part is positive, both in the positive direction and negative direction of z axis. It is positive because it is dz square, and then we have a ring in the xy plane which is negative, and so this annular ring can easily overlap with the plus x minus x plus y minus y. So this orbital is suitable for overlap with the dz square orbital. Similarly, next combination is sigma x plus sigma minus. So in the x direction, both in the positive and negative, it has got positive sign, and y direction it has got the same magnitude but negative sign. So you see plus x minus x plus y minus y, opposite sign, and so this is suitable. This is more like the dx square minus y square orbital, right? So dx square minus y square, this part is positive, this part is negative. And finally we have this orbital which has got s orbital symmetry, this orbital which has got dz square like symmetry, this combination it has got dx square minus y square like symmetry, and finally we have other three contribution. Here it is only plus z and minus z are involved, and they are of opposite sign, so plus z and minus z, and no other x and y is not contributing. So this orbital is suitable for overlap with the pz orbital, because pz orbital looks like this. Similarly, this thing has got only in the x direction, plus x and minus x. So this is suitable for overlap with the px orbital, and this is suitable for overlap with the py orbital. So we find there are 6 ligand group orbitals which are mathematically produced, and out of these 6 ligand group orbitals, 2 ligand group orbitals are suitable for overlapping with the so-called EG orbitals of metal, which are dz square and dz square minus y square orbital. one ligand group orbital is suitable for overlap with the s orbital of the metal, and 3 other ligand group orbitals are suitable for overlap with the pz, px, and py orbitals. And in symmetry jargon, these p orbitals are called T1u orbital because they are ungerade, right? T means triply degenerate, 1 has got some other connotation, and it is T1u. So p orbitals, px, py, pz, they are called T1u orbital. T means triply degenerate, U means ungerade, because this is actually not with respect to symmetry or inversion, it changes sign, so it is not gerade, it is ungerade, right? So we have T1u orbitals, 3 T1u orbitals, px, py, pz. We have 2 EG orbitals, which are dz square and dx square, and 1 s orbital, which in symmetry jargon it is called A1g orbital, which is fully symmetric orbital. A means full mono, there is no degeneracy, single, and 1g means fully symmetric, right? Gerade and fully symmetric. This is gerade because with respect to inversion, it doesn't change the sign, so it is a gerade orbital. So 6 ligand group orbitals are A1g, which mixes with the s, the 2 EG orbital, which mixes with dz square and dx square, and 3 T1u orbitals, which mix with the pz, px, and py orbitals. So I will stop it here. In the next class, we shall take forward this MO theory. Thank you.
So,
Yes.
so we will take a practical class this Wednesday.
Yes, I have confirmed at the beginning of this class that this Wednesday I shall be taking the practical class. Okay.
Okay, sir. Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.